So Unit 5, we are doing Target 5.5, which actually is Section 5.6. Section 5.6 in your textbook, but it's Target 5.5. They can get a little confusing. So we're going to talk about growth and decay, and the outcome is I will solve differential equations that are involving growth and decay. So we need to talk about what are differential equations. And I've really kind of already taught this to you a little bit, so it's just going to be reinforcing this concept, solving differential equations using separation of variables. So we want to express y prime. You'll be given a problem. You want to change out the y prime if it has a y prime in it and put dy dx. Then you're going to rewrite the equation so that the variable occurs on one side. Each variable occurs on one side. So you want the y's on the left and the x's on the right. And then you're going to integrate both sides with respect to its variable. So the left side you'll integrate with respect to y. The right side you'll integrate with respect to x. And this is where you're multiplying the dx to the other side. And then you'll rewrite. So you're going to separate, get your y's on the left, x's on the right. Then you're going to integrate both sides and simplify. So like I said, we've already done some of this already. I've been kind of prepping you, getting you ready for this so that you would be ready to go when we got here. So we've already done some of these problems. Solve the differential equation. So first thing I'm going to do is I'm going to replace the y prime with dy dx. And then I'm going to multiply the dx over. All right, and you don't have to put this in parentheses, but you can. So now that I've got the y's on the left, the x's on the right, I'm going to integrate both sides. And in between the integral sign and this bookend, there's a 1 right here. So the antiderivative of 1 in terms of y is going to be a y. And then we're going to integrate on this side in terms of x. So the antiderivative of x, remember you raise a power, so x to the second divided by 2, plus the antiderivative of 2 will be 2x. And then you have to put on that plus c. You don't need the plus c on the left side because you're just going to put a plus c on the right, which will represent both of your plus c's. And so then there's your equation. You've got y equals x squared over 2 plus 2x plus c. You've solved the differential equation. Next one, number 2, just rolling right along. Solve the differential equation. So again, I'm going to replace the y prime with dy dx. So now I need to get the y's on the left, so I'm going to multiply the y over here, so that'll be y dy, and I'm going to multiply the dx over on this side. So basically I cross multiplied, right? I cross multiplied. So now I can integrate both sides. So the antiderivative of y in terms of y, this is reversing the power rule, so I'm going to raise the power to a 2 and divide by 2. Then on this side, the antiderivative of 5x, keep the coefficient 5, and do the antiderivative of x, which means I raise a power to a 2 and divide by 2, and then put a plus c. And then the only thing I need to do extra to this one is I need to solve for y. So the first thing I would do is I'll multiply the whole equation by 2 because I want to get rid of these fractions. So y squared would equal 5x squared plus 2c. And then I would solve for y, which that would mean taking the square root. So when you take the square root, you know you have a positive and a negative answer for 5x squared plus 2c. So there's my answer. I just don't know at this point whether to take the positive or the negative answer. I would need more information, whether I would need the positive or negative answer. And that would be given an initial condition that we have been given in the past that you've been doing. And so we'll talk more about that when we need to do those kind of problems. But here we're just solving the differential equation for y and keeping the plus c in there. All right, just a few more practice problems of this kind. Solve the differential equation. So again, I'm replacing the y prime with dy dx. And I'm even going to write that as x to the 1/2 over 3y. So now we're going to cross multiply. So 3y dy, because I'm basically multiplying the 3y over here, multiplying the dx on this side. So now I'm going to integrate both sides. The antiderivative of 3y in terms of y would be 3y squared over 2. The antiderivative of x to the 1/2, well, we're going to raise a power, which means I add my denominator to my numerator, so it'll be x to the 3/2. Instead of dividing by fraction, remember we multiply by the reciprocal. So I'm going to multiply by 2/3 and then plus c. So I've just done the antiderivative of both of those. And now I'm going to get rid of my fractions. So I'm going to, basically I'm solving for y. So let me first, let's multiply by 2/3. That'll get rid of my coefficient. So I'm going to multiply everything by 2/3. So that'll be y squared equals 4/9 x to the 3/2 plus 2/3 c. Then to solve for y, I got to take the square root. So I know I'm going to have a positive and a negative answer. So y equals a positive and a negative square root of 4/9 x to the 3/2 plus 2/3 c. And you can't simplify that. And still, like in the last problem, I don't know whether it's positive or negative because I don't have an initial condition to tell me. So that's solving that differential equation, just making them a little bit harder as we go. All right, so this one, replacing the y prime with dy dx. So I need to separate my variables. So I need my x's on the right. So I need to move the dx over here and have x dx. But I need to move this 1 plus y, so I need to divide it. So it's going to be 1 over 1 plus y dy. So I've got to divide that over to the other side. So I divide the 1 plus y to the other side, which makes it in the denominator, 1 divided by 1 plus y dy. And then I multiply the dx over here to make x dx. Now I integrate both sides. All right, so this one is a natural log problem. It's the natural log of 1 plus y. All right, so that is because the numerator is the derivative of the denominator. So the derivative of 1 plus y in terms of y's would be 1. So I've got the derivative divided by the function. So this is f prime divided by f. So that's the natural log of f. And then on this side, the antiderivative of x would be x squared, raise a power, divide by your new power, and then plus c. Okay, so now I need to solve for y. So here's what we need to do to get rid of these and solve for y. The easiest thing is to, since this is ln, we need to use an e. So let's make both of these the exponents on e. So then this will be e raised to this power and e raised to that power. Okay? So now these two things, these are inverse operations. So these cancel each other out. So I'm left with the absolute value of 1 plus y. So then over here, I've got e raised to the x squared over 2 plus c. This is all the exponent. Now remember, when you multiply powers, like if I have 5 to the second times 5 to the third, when you multiply powers, you add exponents. That would be 5 to the fifth. So if I start out with already a sum added together, I can break this apart into a product. So if I started out with 5 to the fifth, then I could write it as 5 to the fourth times 5 to the first, because when you multiply powers, you add. So I could just break this up into any combo I wanted to. So this over here is adding the x squared over 2 and the c. So I can break this up into e to the x squared over 2 times e raised to the c. Because if you're thinking about it going backwards, when you multiply powers, you add your exponents. And so I would get this up here. So I'm just reversing it. Since I have a sum in my power, in my exponent, I can write it as two separate powers with the base of e. Okay? All right. Then this e to the c becomes my new constant. So e to the c here, that could become a new constant. And then, so I could just call it big C. And then I'd have e to the x squared over 2. So now that I've got this big C right here, it can take on whether it's positive or negative. So now I can take these bars off. So 1 plus y, and then I can move the 1 over. So this would be my final answer, minus 1. So C times e to the x squared over 2 minus 1. All right, so this C can be positive or negative, so that's why I'm able to take those bars off. Okay, so this is the differential equation for the problem I have. All right, it's a little bit different. So when you did your antiderivatives, you had natural log. So whenever you have natural log, that's when you want to raise these things, make these the exponents to your e, so that cancels. And then anything that's adding over here, you separate into 2 and make it a product. okay? And then always the e to the c, because you'll always have a plus c, so you're always going to be multiplying by e to the c. Always make that a big constant times this other term. And then you can take the bars off. All right, so that's what you do every time on one like that. All right, so then this is the last one of this kind, I think, and this is a little bit more difficult here. So first thing I need to get rid of this. Let's move this over to the other side. So y prime is going to equal 100x minus xy. And then replace the y prime with a dy dx. And then I'm going to have to be able to separate my y's from my x's. So I need to get these guys apart from each other. So I can factor out an x out of this expression. So I've separated my x's and y's. So now I can move the y term over to this side. So I'm going to divide by 100 minus y and keep the dy on that side. And then I'm going to multiply the dx over to this side. All right, so I divided the 100 minus y and I multiplied the dx over. So now I'm going to integrate both sides. All right, this is also a natural log over here. However, the derivative of my denominator is actually -1, and I don't have a -1 up here, so that's going to make this antiderivative negative. All right, so in order for this to be derivative over function, I would need to have -1 over 100 minus y, because the derivative of 100 minus y is actually -1, and there's not a negative up here, so that means the antiderivative is going to have that negative in it, just to say that again. All right, the antiderivative of x is going to be x squared over 2 plus c, so now I'm going to do the same thing I did before, except I might want to move the negative over to the other side just to make it a little easier. So that would be the natural log of 100 minus y. Just distribute and multiply the negative to the other side. You're basically multiplying the whole equation by -1. So that's going to make negative x squared over 2 minus c. And so then I would do the process again of doing the e. I would make these guys the exponent on e. So again, those cancel. That's going to leave me with the absolute value of 100 minus y. Over here, we have a subtraction. Now, when you have a subtraction, remember, you've got division. So this is going to be e to the negative x squared over 2 divided by e to the c. Now, this 1 over e to the c, that can still become your big C. So this right here can still become a big C, e to the negative x squared over 2. Then I can take these bars off. And I'm solving for y. And so then if I subtract 100, and then I would multiply through by a negative. So multiplying through by a negative, you can write it as negative c, or you could just leave it c. And this would be my final answer. Because c is a constant, it can absorb that negative sign. All right. And so there would be the solution to my differential equation that I started with. So the trick on this one was we needed to get the xy, get the y prime by itself, and then once I move the xy over here, you have to separate your x's from your y's, and we've got this term here that has both an x and a y in it. So something had to be factored out to separate the x's from the y's. And since both terms had an x, that's what I factored out. If both terms had a y, I would have factored out the y. All right, and then you're able to separate and integrate both sides. Again, you end up with natural log. That's when you make these guys both the exponent on e, break this one up to where you've got your big C, take your bars off, and then finish solving for y. That's kind of the process that happens every single time for these. All right, so why did I lead us through all that? Okay, this leads us into growth and decay models. All right, this says the rate of change of y, of the variable y, which a rate of change of y is a derivative, so that would be y prime, is an equal sign, proportional to the value of y. Now, proportional is where I need the constant of proportionality that you learned about in Advanced Algebra 2 or Pre-Cal 1, to the value of y. So proportional means k times y. So we've got the rate of change of the variable y, which is y prime, is proportional to y. So it equals k times y, this constant of proportionality multiplied by y. So what I'm going to do is I just took this sentence and translated it into math symbols. Now I'm going to take this sentence and do exactly what we were doing in these previous examples. So I'm going to replace the y prime with dy dx. And now I am going to separate the variables. So I'm only going to move the y over. So I'm going to divide the y, and I'm going to multiply the dx over here. Okay? So I left the k. Instead of dividing by k times y, I just divided by y. So I have 1 over y dy, and then multiply the dx here, so k times dx. Now we integrate both sides, just like we've been doing. The antiderivative of 1 over y is ln of the absolute value of y, because that's derivative of a function. The antiderivative of k, that's just a number. A constant of proportionality is just a number, a value. The antiderivative of that in terms of x's is going to be k times x. Just like the antiderivative of 3 would be 3x. The antiderivative of k is going to be k times x, and then plus your c. So now we're going to do like we've been doing. We're going to, since it has an ln in it, natural log, we're going to take both of these, the left side and the right side, and we're going to make those the exponent on e. So now this can cancel on this side, so that leaves me the absolute value of y. Over on this side, since it's addition, I'm going to break it up, so this will be e to the kx times e to the c. Because it's an addition, that means I have a product, because when you multiply powers, you add your exponent. So we're just reversing that idea. This e to the c becomes my new constant, big C. And then over here, that I can take the bars off because this constant now will absorb or take on any positive or negative values. So this is the equation I get. So that means anytime you start with this equation, y prime equals ky, or it might be written v prime equals kv, as long as it's the derivative and then the same variables on the other side. So this could be m prime equals km, or a prime equals ka. So as long as the variables match, you have your derivative on the left and then the constant times the function itself without the derivative. These are all the same equation, just with different variables, different letters. When that's the case, then your letter, whatever your letter that was repeated, so in this one it's y, and this one would be v, and this one it would be m and a. The answers to all of those is that letter equals c e to the k times x. All right? That's what you get every single time. So no matter what it starts with, if it starts with a prime equals k times a, then my solution is a equals c e to the kx. So every single time, the algebra that takes you from this equation always leads you to this equation here, which is the growth and decay model. Okay, that is the growth and decay. So basically, basically this is, I'll just leave it. So basically this is the differential equation for growth and decay. So when you solve this differential equation, this is always your solution curve. Okay? All right, so this is what I just explained right here. So theorem 516, if y is the differential function of t, they used a t instead of an x, such that y is greater than 0, and here's this little equation, y prime equals k times y for some constant k, then you always end up with this solution. Y equals c e to the kt. They just used a t instead of x. All right, so this is the growth and decay model. So c is your initial value of y. So the constant c always ends up being your initial population, because growth and decay is like amount of bacteria or amount of a radioactive element, or the number of people in a population. All right, so c, this constant, is always the initial amount of the population. So 0c is always the starting or initial amount for the quantity that you're working with. All right, k is the proportionality constant. Now, exponential growth occurs if this k constant is positive. You have growth. If that K constant is negative, then you have decay. All right, so that's what's happening. So if this exponent K, if he's a positive number, if he's positive number, then that is growth. If that K is a negative number, then you have decay going on. All right, so that's all of your content video, and then I will do an example video for the rest of the growth and decay problems.